Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. So I want you to imagine firing a high-caliber bullet directly into a massive hanging block of wood.
Right, the classic example.
Exactly. And if you remember your high school physics class, you probably know that this is supposed to be, a perfectly simple, elegant math problem.
On paper, sure.
Right, on paper. But what if I told you that in the real world, relying on that exact type of textbook math is actually the #1 reason multi-million-dollar structural designs completely catastrophically fail?
Yeah, it's a huge issue.
It really is.
Yeah.
Today, we are going on a deep dive into something that, frankly, keeps mechanical and structural engineers awake at night. We're talking about the chaotic, unforgiving world of impact dynamics.
It is definitely not as neat as the textbooks make it seem.
No, it's messy. So our mission for you today is very specific. We are going to break down the biggest pain points and the actual real-world physical issues you run into when designing structures to withstand violent collisions.
Because you will run into them.
Oh, inevitably.
Yeah.
We're going to call it the common, almost instinctual misconceptions that just keep screwing up structural designs, and then we're going to walk through a step-by-step approach so you don't fall into those same traps.
Yeah, getting to the practical side of things.
Exactly.
Oh.
We want to show you how to actually optimize your design, not just on a pristine chalkboard, but out there in the unpredictable real world.
It's an incredibly vital topic, and, well, I'm really glad we are tackling it today. To make sure we are all starting from the exact same baseline, let's firmly define what we mean when we say impact.
Good call.
In its simplest mechanical definition, an impact occurs when two or more bodies collide, generating relatively large impulse-type forces at points of contact for extremely short periods of time. And I really want to emphasize that last part, the short periods of time. That element of time is the crucial differentiator here.
Right.
An impact is not a gradual, static load that a structure can slowly distribute. It's a sudden, hyper-violent transfer of energy that basically forces the material to react before it even has time to fully register what's happening.
That's a really great distinction. I guess it's the difference between gently setting a 50-pound weight on a glass table versus dropping that exact same 50-pound weight onto it from a second-story window.
Exactly. Same mass, entirely different physics.
Right. So let's start with the most common trap I see engineers fall into. I call it the billiard ball misconception.
I like that name.
Because, when you first learn physics, essentially every impact is treated like a perfectly smooth, perfectly solid billiard ball hitting another billiard ball on a completely frictionless pool table.
Right, and it's easy to see why we start there. I mean, that elementary analysis actually traces all the way back to an experimental observation made by Sir Isaac Newton.
Oh, wow, really?
Yeah. Newton observed that when two bodies collide directly, their relative velocity after the impact is in a constant ratio to their relative velocity before the impact, just acting in the opposite direction.
Okay, that makes sense.
We call this constant ratio the coefficient of restitution, which is usually designated in the equations by the lowercase letter e.
Right, the little e.
Exactly. And when you combine that restitution coefficient with the law of conservation of linear momentum, you get the foundational classical math for simple, rigid impacts.
And just to put that math out there in spoken terms so we can sort of visualize the formula, it looks like this. It's u prime minus x prime equals negative e multiplied by the difference between u and x.
Spot on.
And then for the momentum side of the equation, it's simply balancing the scales, right? So mu times u prime plus mx times x prime equals me u times u plus mx times x.
Exactly. You are just cleanly balancing the masses and the velocities before the collision with the masses and velocities after the collision. It's clean, it's elegant, and it assumes that the bodies involved are completely, perfectly rigid.
Which is incredibly tempting to rely on. I mean, it's that classic ballistic pendulum model we mentioned at the very beginning with the bullet and the wood block.
Right.
If you know the mass of the bullet and you know the mass of the wood block hanging from the string, you really only have to care about the initial velocity of the incoming bullet and the final swinging velocity of the combined embedded mass.
You basically just skip over the middle part.
Yeah. You get to completely ignore the incredibly complicated, chaotic, messy forces happening during the fraction of a second when the bullet is actually tearing into the wood fibers and stopping.
Which is very convenient for a math test.
But here is where I have to push back on the textbook.
Yeah.
When does this highly convenient, perfectly elegant math completely fall apart for you as a real-world engineer? Because, frankly, nothing in the real world is perfectly rigid.
Right. It falls apart the exact moment the collision generates vibration. What's fascinating here is how the Hertz theory of impact explains this exact physical boundary. The Hertz theory gives us a mathematical way to look at two solid elastic spheres colliding. It tells us about the localized pressure distribution and the exact duration of the contact between them.
Okay.
But the theory has a very strict, highly specific limitation. It is only mathematically valid if the duration of contact is long in comparison with the period of the fundamental mode of vibration of either sphere.
Wait. Let me make sure I'm visualizing this fundamental mode correctly. You're saying that basically every object naturally wants to vibrate at a certain frequency.
Yes.
And if the duration of the crash is actually faster than the object's natural ability to vibrate, all hell breaks loose.
Precisely. If they hit and stay in contact long enough,
Meaning it's a relatively slow pushing kind of impact.
right, exactly, then the simple rigid body math works fine, the energy moves smoothly. But if the impact is sharp and fast enough to excite internal vibrations in the structure,
Which is basically what happens constantly in real-world engineering.
oh, constantly. In that case, we have to throw out the rigid math and look at the vibration-energy ratio. Because if vibration is generated, the kinetic energy of the colliding bodies doesn't just stay as simple translational energy, cleanly moving the object from point A to point B.
So where does it go?
A massively significant portion of that energy gets instantly converted into internal vibrational energy. The object effectively rings like a struck bell.
Oh, wow.
And once your structural beam or your chassis is ringing, that simple rigid body math is essentially useless.
So if real things ring, we obviously aren't just dealing with perfectly rigid spheres floating in a vacuum. We're dealing with flexible steel plates, massive I-beams, actual complex structural assemblies.
Yeah, the real stuff.
And this is exactly where I see designs consistently fail. It's what our sources call the single degree of freedom trap.
Yes, the single degree of freedom trap. When we move from rigid bodies to something like an elastic plate, the physics changes dramatically and, well, violently. Imagine a solid steel sphere striking an infinitely extended elastic plate. The impact doesn't just uniformly push the plate downward. It creates high-speed flexural waves.
Okay.
And the math behind this shows that the half period of these flexural waves is exactly equal to the duration of the impact itself. The total kinetic energy from that striking sphere is aggressively split up.
Split up into what?
It becomes both the kinetic and the potential energy of the wave motion physically traveling outward through the plate.
Okay, so the usual analogy here is dropping a stone into a pond,
Right.
seeing the ripples move out. But to really capture the violence of this, I think it's more like dropping a massive boulder onto a frozen pond.
That's a good way to look at it.
Because the ripples aren't just softly moving water, you know. They are shock waves, violently bending, twisting, and snapping the ice as they travel outward at supersonic speeds.
Yes.
That's what's actually happening to your structural steel. It's this chaotic wave of strain
Huh.
echoing through the material matrix.
That is a much better way to visualize it. And it leads us directly to the biggest, most critical pain point highlighted in our deep dive today.
Let's hear it.
There is a fundamental rule that engineers ignore at their absolute peril. A structure can seldom be treated as a single degree of freedom system with any degree of reliability.
This is huge.
It really is.
Assuming a steel beam just bends in one simple, uniform arc, like a diving board bending down under a diver's weight and smoothly popping back up, is a fatal misconception.
It's just not how metal behaves under shock.
Right. Our sources show that even relatively small masses moving at relatively low velocities can develop surprisingly massive localized bending strains in beams. And the reason is precisely because they excite so many different modes of vibration simultaneously.
Exactly.
The beam isn't just bending nicely in the middle, it's rippling, it's twisting torsionally, and it's vibrating in multiple complex harmonic ways, all at the exact same time.
Right. And when you realize that the structure is rippling in all these chaotic high-frequency modes, you can see why engineers immediately look for a quick, intuitive fix.
Oh, I know this one.
Yeah. And the most common quick fix is always external damping.
Yep.
They look at the design and think, well, if the structure is vibrating and winging, I'll just add external dampeners to absorb the shock.
Right. I've seen it 100 times. Can't we just slap some massive rubber shock absorbers on the engine mounts or the frame connections and call it a day? The rubber will just soak it up.
You would think so. I mean, it feels intuitively correct.
Yeah.
But the facts counter this with two incredibly crucial points that prove why that instinct is just flat out wrong.
Okay, lay 'em on me.
First, external damping does almost absolutely nothing to reduce deflection and strain in the higher, more complex vibration modes.
Really?
Pretty much. A big rubber mount might slow down the primary visible bounce of that diving board we talked about, but it does virtually zero to stop the high-frequency internal ripples that are actually tearing the crystalline structure of the metal apart.
Hold on, that completely defies common sense.
I know it does.
If I put a massive, highly engineered rubber shock absorber on a steel mount, you're telling me it does literally nothing to stop the metal from tearing? How is that even possible?
Because of the speed of the wave. Which brings us to the second, even more critical point for the lifespan of your design.
Okay.
Impacts produce incredibly sharp, virtually instantaneous initial rises in strain. These spikes happen so fast that they are almost completely uninfluenced by external damping.
Wow.
By the time the external rubber dampener even physically compresses enough to register that an impact has occurred, that massive initial spike of flexural strain has already blasted completely through your metal structure.
So the wave outruns the dampener's ability to react. So by the time the rubber squishes, the microscopic damage inside the steel is already done.
Yes. The rubber catches the slow aftermath, not the violent initial shock. And if this structure is part of an industrial machine or a vehicle chassis that gets hit repeatedly over its operational life, you have just created a massive, highly dangerous, and often completely overlooked fatigue problem.
That's terrifying.
It is. The material is experiencing these violent microstrains over and over and over again, and your expensive external damping system is completely blind to it.
So what's the fix?
The only thing that can actually help make those higher destructive vibration modes safely aperiodic is internal viscous damping.
Meaning the inherent property of the material itself to dissipate that high-frequency energy internally.
Right.
So it's turning that microscopic friction into heat rather than relying on a bolt-on accessory.
Precisely. You have to rely on the material's internal architecture.
Okay, so if external damping is basically too slow to catch the shock waves, and elastic waves are incredibly chaotic, what happens when we just hit the structure harder?
Things get worse.
Right. What happens when the impact is so violent, so severe, that we blow right past the elastic limit of the material entirely? We are no longer talking about bending waves that eventually snap back into place. We are transitioning into permanent plastic yielding. And this brings us to what I call the critical velocity trap.
This is where the physics of materials gets truly unforgiving. To understand it, we need to look at longitudinal impacts on long bars.
Okay.
When a metal bar is struck and remains in an elastic state, the stress waves move through it in a very predictable mathematical way. The internal stress and the resulting strain are directly proportional, and they are related by a constant known as Young's modulus of elasticity.
Right, and the math for that, read naturally, is just sigma equals epsilon multiplied by E.
Exactly.
Where sigma represents the stress, epsilon represents the strain, and E is Young's modulus. It's a perfectly linear, highly predictable relationship. You put stress in, you get proportional strain out.
Yes. It's a clean, straight diagonal line on a graph. But once the impact force is so high that it forces the material to permanently yield,
Right.
once you cross over that threshold into plastic deformation, that straight line completely disappears. Young's modulus goes entirely out the window. It no longer applies.
Wow.
And the massive pain point here for structural designers is that the wave velocities in the plastic phase plummet drastically. Plastic strain waves move much, much slower through the material than the elastic stress waves do.
Wait. I'm stuck on this idea.
Mm.
Why does a slow plastic wave matter so much? If the metal is yielding, isn't it just, denting?
It matters because of the critical velocity of impact. Think about the physical variables here.
Okay.
The plastic wave velocities approach zero as the strain is indefinitely increased, but your impact velocity, the speed of the object hitting your structure, is an independent variable. It can just keep getting faster and faster.
I don't see where this is going.
Right. Because of this mismatch, you will eventually reach a mathematical point where the incoming impact velocity significantly exceeds the velocity of the plastic strain wave trying to carry that energy away from the impact site.
So it just backs up.
When that happens, the kinetic energy literally cannot physically move away from the point of contact fast enough. The material can't distribute the load.
So what's the physical result of that trapped energy?
The continuity of the material is violently, instantly broken. It doesn't just dent, it doesn't just bend, it ruptures completely right at the point of impact.
Okay, I think I have a good way to visualize this.
Let's hear it.
It's like the old parlor trick where you try to pull a table cloth out from under a fully set dining table.
Oh, yeah.
If you pull the cloth steadily, the energy moves through the fabric and you slowly drag the dishes off the table. But if you yank that cloth with an immense, sudden, violent velocity, a velocity that exceeds the critical velocity the fabric's weave can transmit, you don't move the cloth at all.
Right.
You just rip a hole straight through the fabric where your hands are holding it.
That's a fantastic analogy. The energy can't propagate, so it just destroys the localized area.
And the really terrifying thing for an engineer here is that your normal instinct doesn't work.
Not at all.
If I have a beam that keeps breaking, my instinct is to just make it thicker, add more steel. But if the impact exceeds the critical velocity, the material simply shears or shatters locally. It doesn't matter how much heavy steel you throw at the rest of the problem, because the rest of the steel never even feels the impact before the front completely shatters.
Precisely. The thickest armor in the world won't save you if the localized material rips before the energy can spread to the rest of the plate.
So what do we do?
Which naturally raises the most important question of our entire discussion, right? If you can't just make the structure thicker, and you absolutely can't rely on simple rigid math, and external rubber dampeners are completely blind to the initial shock, how is the design engineer supposed to actually survive this? We can't just defy physics.
Which perfectly sets us up for the final leg of our journey today, the step-by-step optimization approach.
The good stuff.
Exactly. Armed with this frankly terrifying knowledge of exactly how and why materials break under dynamic load, how do you actually optimize your design in practice to survive?
The solution lies in shifting your entire engineering mindset to what is called the energy method.
The energy method, okay.
Instead of just looking at elastic limits and trying to keep a structure perfectly stiff, you have to embrace deformation. Engineers must look at the total energy of absorption required to cause plastic deformation all the way up to the ultimate point of rupture.
So we want it to deform.
Yes. You are no longer designing a rigid, immovable wall. You are designing a metallic sponge. Your goal is to accurately calculate how much total kinetic energy the volume of your material can soak up through permanent ductile deformation before it finally snaps.
Our sources actually have a brilliant, highly specific, real-world example of this that perfectly illustrates the math. Let's walk through it slowly so we can really see how this optimization works.
Let's do it.
Imagine you have a tension bar made of medium steel. The material properties of this specific alloy tell us that it can absorb about 500 foot-pounds of energy per cubic inch of volume before it physically ruptures.
Okay, 500 foot-pounds per cubic inch.
Now let's look at two totally different dynamic impacts. In the first scenario, we have a heavy 200-pound body moving at a speed of 80 feet per second.
All right, so if you calculate the total kinetic energy of that moving body, which is 1/2 mass times velocity squared, that object packs exactly 20,000 foot-pounds of kinetic energy.
Right. That's a lot. Now, let's say your engineered steel bar is relatively small. Let's call it 10 inches long and 1/2 inch in diameter.
Pretty small.
If you calculate the volume of that cylinder, it's only enough physical material to absorb about 1,000 foot-pounds of energy total.
Oh.
Yeah. So you have an incoming payload of 20,000 foot-pounds of energy slamming into a bar that can only soak up 1,000 foot-pounds. The result is obvious.
The bar is completely and violently ruptured. It didn't have enough sponge to soak up the water.
Exactly. But look at the second scenario to see how the variables shift. Suppose the incoming moving body only weighs 50 pounds, and it is moving much slower at 30 feet per second.
Okay, so if you run the kinetic energy calculation on that, the total energy payload is only about 700 foot-pounds.
And since our little 1/2 inch steel bar has enough volume to absorb 1,000 foot-pounds of energy, it actually survives the impact.
Wow.
It will stretch, it will deform permanently. It will look completely warped and ruined to the naked eye.
But mathematically and physically, it will not break. It holds the load.
Yes. So optimization using the energy method isn't about achieving infinite stiffness. It's about meticulously balancing the total physical volume of your ductile material against the total anticipated kinetic energy of the impact. You literally just need enough cubic inches of yielding material to safely soak up the energy payload.
That is the theory, and on paper, it works beautifully. It's how crumple zones in cars are engineered, for instance.
Right.
But we have to address the fatal design flaw that routinely ruins this beautiful optimization in the real world.
Ah, yes, the invisible killers of structural integrity. Let's talk about what ruins the sponge.
The most common real-world screw-up that completely nullifies the energy method is the presence of stress concentrators.
Stress concentrators.
Specifically, I'm talking about physical notches, sharp internal corners, and poor quality welds.
Okay, why are those so bad?
Think back to our perfectly machined steel bar that can absorb 500 foot-pounds per cubic inch. That mathematical assumption completely relies on the entire bar stretching uniformly.
Right.
It assumes every single cubic inch of that metal is doing its fair share of the work, sharing the stress across its entire geometric length.
But what if there is a tiny, almost microscopic sharp notch cut into the side of the bar? Say a machinist made a mistake or a tool slipped during manufacturing. What happens to the energy then?
The physics of the energy flow changes completely. You can think of stress moving through a material almost like water flowing through a pipe.
I like that.
When that force hits a sharp notch, the flow is violently disrupted, and the stress lines bunch up and concentrate incredibly heavily at the very tip of that tiny notch.
Oh, man.
Because the stress is exponentially higher there, the material in the immediate neighborhood of that notch yields first. It deforms plastically and then quickly reaches its rupture point, while the rest of the pristine, untouched steel bar remains completely unstressed.
So the whole thing fails.
Yes. Because the notch acts as a localized weak point, the catastrophic break occurs right there instantly. The bulk of your carefully calculated, beautifully engineered volume of steel absorbs exactly zero energy.
Because it never even got the chance to.
Exactly.
The chain broke at the weakest link before the rest of the links even felt the pull.
Yeah.
And the exact same thing happens with a bad weld.
Without a doubt. If you take two unnotched, perfectly optimized steel bars and join them with a porous, poorly penetrated butt weld, the rupture will happen entirely at the weld interface.
Right.
The full energy absorption capacity of the rest of the bar is totally wasted. Your beautiful, theoretically perfect design optimization on paper means absolutely nothing if stress concentrators are introduced during the actual fabrication process.
So to synthesize all of these complex technical takeaways and, directly answer the biggest question you probably have right now, how do I ensure my design actually survives a violent impact?
The million-dollar question.
The answer is a strict three-part checklist based on everything we've uncovered today. Number one, do not use single degree of freedom models for dynamic impacts. Your structure is not a simple rigid pendulum. It is going to ring and vibrate in wildly complex ways, and you absolutely must account for high-speed flexural waves.
Crucial step.
Number two, do not rely on external rubber damping to save you from the initial strain spikes. The shock wave is simply too fast. External dampeners will be blind to it, and you will end up with... And number three, if you are designing for severe impacts that push past the elastic limit, use the energy method. You have to balance your total ductile volume against the kinetic energy payload. But, and this is the big but. Exactly. Yeah. And this is the most important part. You have to vigorously protect that total energy absorption capacity by ruthlessly eliminating any notches, sharp geometric corners, and bad welds from your manufacturing process.
It really highlights how deeply interconnected theoretical physics and practical shop floor manufacturing truly are. You simply cannot have one without the other and expect to survive a dynamic impact. A brilliant mathematical model is totally useless if the welder had a bad day.
Exactly. And I think that dynamic leaves us with an incredibly fascinating final lingering thought to mull over as we wrap up. We've learned today that a single microscopic notch or a hidden bad weld can completely utterly nullify the energy absorption capacity of a massive, perfectly calculated steel beam.
It's sobering.
It is. The entire multi-million-dollar structure fails simply because the immense kinetic energy found a single, localized weak point to exploit. It really makes you wonder,
About what?
Beyond just structural steel, what invisible notches, whether they are single points of failure in our digital networks, bottlenecks in our supply chains, or even hidden communication breakdowns in our organizational structures, are lurking around us right now, just waiting for the right external impact to cause a catastrophic total system failure.
That's a great point. They're everywhere.
It's a question every designer in every field needs to be asking themselves. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.